In one pass, this machine will reduce the thickness by only a very small amount. So we'll reduce the gap between the rollers and put the metal through again. Right, let's see what that's done to the grain structure. The cold-rolled piece of metal is the one at the top. Can you see the difference? We seem to have changed the shape of the grains. They've become elongated. We can get a better idea of what's happened in a diagram. First, we'll look at the grain structure of the metal before it's deformed. Here, the grains are normal. But as the metal is squashed between the rollers, you can see how the grains become elongated and distorted in the direction of rolling. The change in grain structure that results from cold working is accompanied by a change in the mechanical properties of the metal. Its hardness and tensile strength increases, while the ductility decreases. After cold working a metal, it's usually heated to a sufficiently high temperature. Let's see what effect heating has on the distorted grain structure. In the case of this particular metal, nothing happens until the temperature reaches about 350 degrees centigrade. Now, at the grain boundaries, new grains begin to form. These grow rapidly until a new, undistorted grain structure completely replaces the old, distorted one. We call this process recrystallization. Now let's see what effect this has had on the mechanical properties of the aluminium. Hardness, for example. Here we're measuring the resistance to indentation of a piece of cold-worked aluminium. How does this compare with the size of the dent produced in a piece of recrystallized aluminium? It's much deeper, so recrystallization has restored softness. And what about the tensile strength? First, the cold-worked aluminium. That needed a force of about 7 units to pull it apart. Now for a recrystallized piece. The force is going to be much less this time. The tensile strength has decreased. If we put the broken bits back together again, we find the recrystallized piece stretched the most, so we've also restored the ductility. However, the resulting properties depend on the temperature at which recrystallization is carried out. If the temperature becomes too high, some of the grains will grow at the expense of their neighbors. This can give rise to properties which are highly undesirable for most engineering applications. A cast copper billet. It's been heated to a temperature of about 700 degrees centigrade. At this temperature, copper is more malleable. It can be pushed through a specially shaped die. And made into a long and heavy tube. This process is known as extrusion. It's the first stage in the manufacture of copper tubing, the kind used by plumbers. Once the tube is cool, it's ready for the next process. With one end pointed, the tube is inserted into a die whose diameter is slightly smaller than that of the tube. The pointed end is gripped and the tube pulled through the die. This has the effect of reducing the diameter of the tube. It's a process known as drawing. In this cutaway section, you can see what actually happens. The tube is drawn over a steel plug and through the die. As it's pulled through, there's quite a reduction in its diameter. Also, you can see here how the thickness of the wall is reduced. Deforming a metal when it's cold like this is known as cold working. A tube is drawn more than once. Each time, both the diameter and the wall thickness are reduced. This has the effect of making the tube much longer. Since we started the tube to this diameter, there can be as many as 10 more draws before the tube is down to size. With each draw, the wall becomes thinner and thinner. In other words, each draw involves a lot of cold working. Well, after all that, have the properties of copper changed? Let's find out how hard and to indentation. On this scale, it has a hardness value of 84 units. Let's compare that with a piece of the cast copper we started out with. It looks much softer. And from the reading, we see it is only 62 units. We can see this difference in hardness by comparing the size of the two dents, cast on the left, drawn on the right. So cold working has had the effect of increasing the hardness of the copper. What effect has it had on the tensile strength? Here we're measuring the drawn or cold-worked tube. We're measuring the force in kilonewtons. That fractured at 27 kilonewtons. Now, to compare tensile strengths, we must measure the force needed to pull a similar piece of cast copper apart. We need a cast tube. But of course, we can't cast a tube. What we can do, though, is machine one from a cast billet. Although this involves some cold working, it's nothing like the amount that's involved in drawing the tube. There. Now for the test. It's much weaker than the drawn tube. Only 6 kilonewtons this time. Since the tubes were the same size, this means that the tensile strength has increased. So cold working has not only increased the hardness, it's also increased the tensile strength of the copper. It's brought about two useful changes in its mechanical properties. But what if we try bending a piece of cold-worked tube? Not all its properties are useful ones. Can you think what could be done to the copper to prevent this from happening? Steel. It's a material with many useful properties. Steel is an alloy of iron and carbon, two materials with only a limited number of useful properties. Take carbon, for example. It breaks very easily. It's weak and brittle. How about the iron? That bends very easily. It's a soft and ductile material. But an alloy of these two, steel, behaves quite differently. It's stronger, and it hasn't bent. Now, steel contains only a very small amount of carbon. In this piece of steel, there's only this amount of carbon. By weight, it's about 1,000th part of the steel. We say it's a 0.1% carbon steel. Other steels are produced which have a different carbon content. Here are 4 of them. What effect do you think the amount of carbon has on the mechanical properties of the steel? Well, let's find out. What we're measuring here is the force required to pull apart a piece of 0.1% carbon steel. We're measuring the force in kilonewtons. That fractured at 61 kilonewtons. 0.25% carbon steel. Let's see what force is needed to pull this one apart. This test piece has the same dimensions as the previous one, so by comparing forces, we can compare the tensile strength. Well, that's where the 0.1% steel fractured. Increasing the carbon seems to have increased the tensile strength. Nearly 80 kilonewtons this time. Let's put those results on a chart. The tensile strength of 0.1% carbon steel is this much. The one containing 0.25% showed a slight gain. Similar tests on the other two steels gave these results. 0.4%, even more strength, and 0.55% carbon, stronger still. So it seems that the more carbon there is in the steel, the greater the tensile strength. But what effect does increasing the carbon have on the other mechanical properties of the steel? Take hardness, for example. Here we're measuring the hardness of the steel containing the least amount of carbon. We're measuring its resistance to indentation. On this machine, reading on the inner scale, we have a hardness value of about 69 units. 0.25% carbon steel. (81 units this time. The higher the reading, the harder the material, so the hardness has increased. Here are those results on a chart. The same test on the other two steels showed a further increase in hardness. The more carbon there is in the steel, the harder it seems to become. At the same time, there's an increase in tensile strength. But what do you think happens to the ductility? Well, we'll leave that for you to find out. This is molten steel. When it cools, it will solidify and grains will be formed. Let's find out what the grain structure of a piece of plain carbon steel is like. We've given this piece of steel a mirror-like finish. Now we're etching it. The steel contains 0.4% carbon. So far, so good, but with the unaided eye, we can't see any grains. We'll have to take a small sample of the steel and view its surface through a microscope. Here it is, magnified nearly 250 times. Let's take a closer look at this in a diagram. In the case of steel, there are two different types of grain. We'll look at each in turn. The light grains, like this one, are made up of iron. Engineers call them ferrite. These give steel the property of ductility. The other grains, like this one, are made up in layers. The white layers are iron. The black layers are a chemical compound of iron and carbon, called iron carbide. Pearlite is the name given to this type of grain. They give steel the properties of hardness and strength. This particular piece of steel is made up of roughly equal numbers of the two types of grain. So far, we've only looked at 0.4% carbon steel. However, steel can be produced with other carbon contents. What effect does this have on the grain structure? We'll start with 0.4% carbon, and let's add some more. Can you see what's happening? The number of pearlite grains is increasing. Now there are no ferrite grains at all. The steel now contains 0.8% carbon. Under the microscope, a similar piece of steel looks like this. You can probably guess what will happen if we now reduce the amount of carbon in the steel. The number of pearlite grains decreases, leaving a lot of ferrite grains. Now there's only about 0.1% carbon left.